Okay, good morning. So we continue the lesson of matrix theory, but a new topic here now. We want to talk about inverse of the matrix. So for example, remember we talked about powers, natural powers of matrices. For example, if I give you a square matrix, I could ask you to calculate or compute a squared, a to the power of 3, but we never talked about negative powers yet. So this is some kind of motivation for negative powers. And that's exactly the same thing we did for numbers. So if you remember, when we wanted to talk about numbers, we defined natural powers of numbers. For example, when I say a number a to the power of 3, it means a times a times a. And then to answer what is a to the power of minus 3, we could define what we mean by a to the power of minus 1. So we define a to power minus 3 as a to power minus 1 to power 3. Okay? But the point is that we need to have a definition for a minus 1 first. Yes, so we define a minus 1. What was a minus 1? What is the definition of minus 1? For example, when I say 2 to the power of minus 3, of course, because you already know, you can just simply do this and then you get the answer 1 over 8. But the definition of 2 to the power of minus 3 is actually 2 to the power of minus 1 to the power of 3. Then the only question is that I need to define what this is, because if I define what this is, then you already know how to deal with positive integer powers. Yes, you just take that thing and multiply it by itself 3 times. So in order to be able to define a negative power of numbers here, for example, 2 to the minus 3, you need to know what 2 to the power of minus 1 means. If I define this for you, then you can also calculate everything with negative powers as well. So the crucial point is to understand what is the 2 to the power of minus 1 means. So what's the definition of 2 to the power minus 1? Yes?
1 over 2.
It's 1 over 2, but that is the one definition. Here we cannot, because I want you to define it in a way that it can be applicable to matrix theory. Because in matrix theory, we do not have 1 over a matrix, we do not have division. So, yes?
The inverse of 2.
Okay, so what's the meaning of the inverse of 2? When I say 2 inverse, it means it's a number when multiplied by the number itself, it gives you what? 1. This definition can be extended to matrix theory, because in matrix theory we have multiplication. Yes? So in the same sense, if I give you a square matrix, by the way, this topic is only for square matrices. If I give you a square matrix and I want to make sense of this symbol, I cannot say it is 1 over A, because then you will ask me what is the meaning of dividing y by a matrix. We haven't defined that operation before. Is that clear? So that is the same idea. It's still, but this way of defining 2 to the minus 1 can also be extended here in some sense. Is that clear? Because this, in the definition that you see for 2 inverse, I am not using division, I am using multiplication. So can you tell me, for example, what is your intuition about, if you are a mathematician, how do you think that using this analogy, and exactly that was the behind the head of a mathematician to define a inverse like this. So what do you think will it be? Yes?
The identity matrix.
So you say that A inverse is the matrix defined in which way?
I mean, if A times A to the
A minus, yes, it becomes
the identity.
the identity matrix. Yes? So we say that this matrix, the inverse of this matrix is defined in this way, so that is the matrix which is multiplied by A, and it gives me the identity matrix. Yes? So I'm not making these things rigorous, but I'm trying to say that this is in the back of the head of a mathematician, try to define A inverse, yes? Because I can just define in mathematics this is A inverse, and then you don't have right to ask why do you define it in that way. You need to wait to see if this is useful theory or not, okay? But that is the idea. We have algebra, number algebra. We want to somehow get ideas from number algebra to be able to extend our new algebra, and that is matrix algebra. Yes? So that is more or less a good intuition about that. But there are some technical problems here, so let us just talk about them. One technical problem is that, do you think the inverse of every number exists? For example, do 2 to the minus 2 inverse exists. 3 inverse exists, yes? By the way, what is 2 inverse? 2 inverse is 1 over 2, because 1 over 2 times 2 is 1. Is there any other number with this property which is multiplied by 2 giving you 1? Is there any other number? No, that is the only. So if I ask you what is this one, you will tell me this is 1 over 2, because 1 over 2 is satisfying this condition, and also you know that this is unique. You cannot find any other number with that property. Yes? But there is some exceptions. Is it possible to say that every number has an inverse? Yes?
I'd say no, because you have a number like 0.
And 0 is the only exception. Yes? So 0 doesn't have any inverse. So when I ask you what is 0 inverse means the number when multiplied by 0 gives you 1. That is the meaning of 0 inverse. Yes? Inverse of a number means the number which when it's multiplied by the number itself, it gives you 1. That's the meaning of an inverse of a number. So when I say 0 inverse, it means that is the number when multiplied by the number itself, it should be 1. But this is not possible, yes? Because whatever this guy is, multiplied by 0 should be 0, and this is not possible. So this is why we say that 0 does not have any inverse. Or technically speaking, we can say 0 is not invertible. Of course, these words are not used in number algebra, but there's nothing wrong about that. So 0 is not invertible. So we cannot find an inverse for 0. Okay? Okay, so that is also a question here in matrix algebra now. Is it possible to find, if I give you a matrix, for example, if I give you matrix 1, 2, 3, and 4, do you think it is invertible? What does it mean? It means, can you find another matrix so that when it is multiplied by this matrix, it gives you the identity matrix?
Yes.
Okay? So this is what I want you to understand. The question is not that simple to answer. It's not simple as this one in the numbers, okay? So the question is this: if I give you a matrix, a square matrix of any order, 2 by 2, 3 by 3, 4 by 4, is it always possible that we can find a matrix which is multiplied by A gives you what? The identity matrix. So that is the question. In case we can find such a matrix, this matrix is called invertible. We will see that the answer is not always one. The answer is not always yes. Sometimes it is possible, sometimes it is not possible. For the cases it is possible, we say that the matrix is invertible, and the matrix that you find with the property when it is multiplied by this gives you the identity matrix is called the inverse of matrix. And sometimes it is not possible, you simply say that it is not invertible. Yes? But here, it was simple. There is only one exception. But here we can have infinitely many matrices which are invertible and infinitely many matrices which are not invertible. Okay? So we want to categorize them. Okay? Is that clear? Okay. So now I think it is time to see the formal definition. Okay? So this is the definition: invertible, or sometimes people call it non-singular matrix. Okay? A square matrix A is said to be invertible or non-singular. Okay? If there is a matrix B such that AB is equal to BA is equal to I, That is another problem when it comes to matrix theory. Okay, so you have to contain both of them. Yes, because in this case, you really don't care. Because you know that number algebra, the multiplication between numbers is commutative. So if this works, definitely the other way around also works. But there is no guarantee that if I can find a matrix that can be multiplied by A from the left and gives me I, you cannot immediately guarantee that, okay, the other way around is also true. Is that clear? Because matrix multiplication is not commutative. So even if you guarantee that, yes, I found a matrix with that property, there is no guarantee that if you interchange the order, it is still the same answer. So this should also be part of our demand or our definition. Yes, definition. So remember, I give you a matrix. I ask you if this matrix is invertible. What do I mean? It means that can you find another matrix B so that both AB and BA are equal to the identity matrix? If you can find that, we say that yes, the matrix A is invertible and B is called an inverse of A. Okay? Because there is no guarantee yet that if this matrix B exists, there is only one such a matrix. Might be there are more matrices. Okay, so this is why at this level I cannot use the article there. I have to use article and. Yes, is that clear? Okay, if no matrix B with this property exists, then A is said to be singular. Or I don't know why I didn't write it, or not invertible. Okay, is that clear? Okay. So we want to study a little bit about these things today, and I want to give you time a little bit to practice on the quiz if you want to. So, example this one. I have written a matrix here, and I want to show that this matrix is a singular matrix. Let us get used to these words. I mean, singular, for me, sometimes it takes time to understand what is singular, what is so invertible or non-invertible is probably easier for us. Okay, we want to show that this matrix is not invertible. Yes? So let us just write that example here. So yes, this matrix, we want to show that it is not invertible. So A is what? A is 1, 2, 3, 6. We want to show that this matrix is not invertible. Okay, let us assume that it is invertible. Okay, if this is invertible, if A is invertible, then there exists a matrix B, say A, B, C, D, such that what? A times B is equal to B times A is equal to the identity matrix. If I can find such a matrix, yes? Okay, but let us see what happens. Let us take A, B and equate it to I. Of course, if it works, we should also be careful about the other way around should also work. Okay, but let us just check the first one. So A times B is equal to I. This then implies that A is 1, 2, 3, 6 multiplied by B, which I assume to be A, B, C, D, because for the time being I don't have any clue for it. And then the identity matrix is just this matrix. Yes? Let us see if we can find that. By the way, the problem is not complicated. The problem becomes complicated if the dimension of the matrix becomes higher and higher. Because then, how many equations you get now? You get 4 equations. Yes, because we have 4 entries. But if you have 3 by 3, I will get 9 equations. For 4 by 4, I get 16 equations. So actually, it becomes computationally costly. So what I do, let me calculate the product. So I already know what to do. Multiply 1 by A. Multiply 2 by C, and then add them up. And I will repeat the process for the other rows and columns. So this becomes B plus 2D, and then 3A plus 6C, and then 3B plus 6D. This is supposed to be equal to 1, 0, 0, 1. If I succeed to do that, then I have to check the other way around as well. This is not guaranteed. And then if both of them will work, then I would say that this matrix is invertible. But according to the claim in the problem, it's claiming that this is not invertible. Let us see why. Okay, if this equality is going to hold, what does it mean? It means that this entry, A plus 2C, should be 1, B plus 2D should be 0, and then 3A plus 6C should be 0, yes? And then 3B plus 6D is equal to 1. If this is going to happen, then this means that this has to happen. Okay, so but how many equations I get? 1, 2, 3, 4. How many unknowns do I have? Exactly 4. But I am claiming this system is not consistent. So even though I have 4 equations and 4 unknowns, my claim is that this is not possible to find A, B, C, and D which satisfy all these conditions simultaneously. Why is that? Yes?
Because, for example, B and D, when added, are supposed to be 0 and 1 at the same time.
B and 2D.
Yeah.
Yes, that's correct. Yes, because you see, we don't know if, of course, this is always possible to find B and D to satisfy this condition, but this is not possible to satisfy this and the last one simultaneously. Yes, because if it is working, I multiply everything by 3, 3B plus 6D becomes what?
0.
0. So on the one hand, you want to have 3B plus 6D 0. On the other hand, you want to have 3B 6D equals to 1. That this is not possible. So even though I had right number of equations and unknowns, this system is called inconsistent. Yes, this system is inconsistent. Yes. And it means that there are no solutions. It means you cannot find A, B, C, and D that satisfy all these 4 equations simultaneously. These 2 cannot happen simultaneously. By the way, for the same reason, these 2 cannot happen simultaneously, yes? But one of them is enough. So this is the end of the story. It's not possible to find such a thing, yes? So this means that this matrix is singular. So therefore, this means that this one and that one. So how should I write? So I just talked about that orally. So in principle, if you want to write it down, you would say that 3B 60 0 and 3B 61 implies that 0 is equal to 1, and that's a big lie, yes? It's a contradiction. So I usually use this symbol saying that this is something contradictory happens. But so therefore A is not invertible. Yes? A is not invertible, or what do I mean? I mean it is singular. By the way, I intentionally gave you an example of a matrix in which number 0 does not play any role. Yes, because I just want to destroy this intuition in your head that it has something to do with 0. But it has something to do with 0, but not in this way. Okay, we will talk about that later. Okay, so that's a big question yet. How can I look at the matrix and before doing this calculation realize that this matrix is invertible or not? But this is not something we have addressed right now. We will talk about that hopefully if we have time later. Is that clear? So this is not invertible. Okay, now let us go to the next one. Here, show that this matrix is invertible. Okay? This matrix is invertible. We have to check it out like this. So let me go to the board. So the matrix is 1, 2, 3, 7. Okay, I want you to understand this example. This is very simple. We want to see if A is invertible or not. Let me just suppress those writings. Assume that it is or it is not. It means if it is, it means that there exists a B such that what happens? AB is equal to BA is equal to Y. Yes? Okay, let us check. Of course, I have to satisfy both of them to make both of them work, but let us start with one of them. So let us see if I can find a matrix B so that this occurs. This happens, yes? So what should I do? Exactly as before, instead of this one, I write this, and I multiply it by A, B, C, D, and I equate it to identity matrix, which is 1, 0, 0, 1, yes? And I do the calculations as before, take the row and column, so it becomes A plus 2C, B plus 2D, 3A plus 7C, and then finally 3B plus 7D. Yes? Yes, am I right? Yes. So this is equal to 1, 0, 0, 1. Then again, I get a system, 4 equations in 4 unknowns. So A plus 2C is supposed to be 1. So if you don't mind, let me write this one below it immediately. So 3A plus 7C should be 0. And then this one should be 0. And this one should be 1, yes? So again, it's more or less the same thing. I have 4 equations in 4 unknowns. But at least you see there are not obvious inconsistencies going on, yes? Because here I have A plus 2C is 1, 3A plus 7C is 0. They are really not that easy to see if they are consistent or not. This is not trivially inconsistent. So we need to solve them. Of course, I have 4 equations of 4 unknowns, but they are decoupled, yes? So these two only encounter A and C. These two are only encountering B and D. So in principle, I do not have 4 equations in 4 unknowns. I have 2 systems. One system only includes A and C, one system only includes B and D. Yeah? So let us solve them. So, for example, A plus 2C is equal to 1, 3A plus 7C is equal to 0. So let me multiply this by minus 3. So then this gives me minus 3, A minus 6C is minus 3, and then I have 3A plus 7C is equal to 0. I add them up, so this is gone. This becomes C, C becomes negative 3. So nothing strange happened, so I was able to find C here. But when I find C, I can put it back here and find A, for example. So then this implies that A is equal to what? This is minus 6. Move it to the other side, it becomes 7. And then I will set up another system. B plus 2D is equal to 0. 3B plus 7D is equal to 1. I multiply this by minus sign again, but let us just do it in our head. I multiply by minus 3 and then add it here. So B is gone, this becomes minus 6D plus D is just D, and this is 0 plus 1 is 1. And when D is 1, B is minus 2. Yes, so it means that we succeeded to find A, B, C, and D. There is nothing strange or wrong going on. So this means that my matrix B is equal to what? A is 7, B is minus 2, C is minus 3, and D is what? D is 1. Yes, so this was my matrix A, B, C, and D. I found these numbers, I put them back, so that's my B. But at this point, technically speaking, we are still not sure that if this is invertible, because we just guaranteed equality between these two. But we have to also have the other equality. Instead of doing the whole calculation for the other way around to see if this is the same matrix, I will take the same matrix I found here and then multiply it in the reversed order to see if it works or not. Okay, now we calculate BA to see if it is working. Okay, so let us multiply this. I take 7 minus 2 minus 3 and 1 and I multiply it by A. What was my A? 1, 2, 3, 7. And what I do, I take this one and multiply it here. 7 times 1 minus 2 times 3. 7 minus 6, which is 1 exactly. I take that one and multiply it here. 7 times 2 is 14. Minus 2 times 7 is minus 14. When I add them, it becomes 0. And I take this one, multiply it here. Minus 3 plus 3. It is 0 again. And I take this one and multiply it here. Minus 6 plus 7 is 1. And that is exactly the identity matrix. So it means that first, I try to find a matrix B that satisfies this. I succeeded. I found the B, but it is not finished because I need to also check the other way around. If AB is I, for the time being, it is not guaranteed that BA is also I, because there is no guarantee that AB should be equal to BA, because we learned that matrix multiplication is in general not commutative. Yes? Okay, so what we can say? We can say that so A is invertible or non-singular. Okay. And B is, at this stage I should say an inverse, but you will see that this is the inverse of A. Yes? The reason is that we can prove later, and this is not hard. If such a matrix B exists, it is unique. If it doesn't exist, okay, it doesn't exist. But if it exists, there is no way for someone to find another way to come up with a different matrix B with this property. Yes? So this means that if it exists, then it is unique. So it is completely valid. If it is invertible, we can talk about the inverse. Yes? And then, if that is the case, I can use a symbol for B. Instead of using B, I show it with A inverse. But A inverse, so for a mathematician to use a symbol for something, that mathematician should be convinced that that thing is unique. Otherwise, A minus 1 is ambiguous. You don't know which one of them is referred by this symbol. So whenever you say you assign a symbol to a mathematical entity, that mathematical entity should be unique. Otherwise, it doesn't make sense. Okay. So I just want you to know that understanding if a matrix is invertible or not is not that easy to understand, yes? So we have to understand. So this is a very good question. How can we know that this is possible or not? To have a matrix which is invertible. Okay, I just can give you a clue. I told you that there is no zeros involved here, but still we saw that this matrix is not invertible. But there is another thing related to a matrix which is called the determinants of that matrix. The determinant of a 2 by 2 matrix is extremely simple. So you just multiply these two and multiply these two. If these two are equal, then the matrix is not invertible. Okay? So here, 1 times 6, 2 times 3, they are the same. So this matrix is not invertible. So for me, we will study this later. By the way, if I improve this to 3 by 3, then the determinant is a whole new story. There is no way to calculate a 3 by 3 determinant like this. So it's more complicated. But yes, we will hopefully reach to that stage at some point that we show that a matrix is invertible if and only if its determinant is equal to 0. So actually the notion, one of the reasons that people got interested in the notion of the determinant of the matrix is because they want to see if the matrix is invertible or not. And invertibility of a matrix is also very important if you want to program a computer to solve simultaneous equations with unknowns. Because you see, the matrix algebra is some kind of algebra that computers are very strong in that calculations, because just this is the multiplication and addition, and they can do it very fast. And then we can use the idea of the inverse matrix to solve equations. For example, might be if you are designing a circuit, electric circuits, because of this Kirchhoff actually rules, you have infinite, sometimes you have hundred thousands of equations and 100,000 of unknowns, so you need to solve all of them, okay? So in that case, you have to have a systematic way of solving, because solving an equation is not, a system of equations technically is not a hard problem, but practically it is really hard problem. So assume that instead of having 4 equations in 4 unknowns, you have 10 equations in 10 unknowns, all of them including all the unknowns, yes? And then you get confused, how can I eliminate them? Of course, technically speaking, I have to eliminate them one by one to reach to a system of 2 equations in 2 unknowns, solve them and come back again, okay? But that would be quite boring and hard. So we have to have a systematic way of solving systems of equations, and the matrix theory can help you to do that. This is among one of the important applications of matrix theory. Okay, is that clear for everyone, more or less what we are doing? Okay.
Hold on.
Yes?
Are only square matrices invertible?
Yes, because we demand both of them. And if these matrices are commuting, they have to be square matrices.
Yeah.
So we don't talk about a rectangular matrix to be invertible or not. So this topic is only for square matrices. Okay, so let us go back to the notes. Here I have another example. Let A be a square matrix that contains a column whose entries are all equal to 0. I hope that you can feel that that matrix is singular. Yes? So that's the content of this example. If you have a square matrix, and in this square matrix you have a column in which all entries are 0. This claims that it is not possible for you to find an inverse for your matrix. Is that clear? I mean, mainly, instead of proving this rigorously, I want you to expand your intuition about the problem, yes? So can you tell me why, or can you just elaborate? You don't need to be very, very mathematically rigorous, but can you see why it is not possible for a matrix such a matrix to be invertible? So this is claiming that, I don't know, for example, my matrix is a matrix, I have some columns, but one column is all 0, yes? And then might be I have other columns as well. So I have a column consisting of all zeros, which I'm claiming, according to the problem, that this is not invertible. Why is that? Why do you think it's not invertible? Yeah, by the way, these problems in matrices are not that hard. So the only hard part is to write a general case. Yes? Because you need to take care about the number of rows and columns. So let us start with something that we know. For example, A, B, C. Let me make it 3 by 3 and 0, 0, 0, and then D, E, F. I mean, if you can say why this is not invertible, technically that's the same problem. I hope that you can feel it. The only difference is that might be the location of this is different, or might be the number of rows and columns are different. But I don't know. I hope that you can feel, I mean, this is not the general case, I agree, but it is not far away from understanding the main problem. Yes? So why this is not invertible? Let us check. You say that this is not invertible. If it is invertible, what does it mean? It means that someone can find a matrix, say X, Y, Z, W, U, S, T, I don't know, L, M, such that this happens, this is 1, 1, and 1, everywhere else 0. Okay, so this is scratch work. I want to understand the problem. Do you think this can happen? Hmm?
Could it be that because there's a 0 on the main diagonal?
Did you come up with that reason? Why? So you are telling
I'm
that
just saying intuitively.
yes, I mean, okay, but do you think that's correct? Yes.
You can have a 0 on the main diagonal and still have an inverse matrix.
Yes.
So
But the point is that this, do you think, of course, if I want to solve it, I can. I have to consider 9 equations, yes, to see that if I can find them. But just the point of this exercise, first of all, even if I could succeed that, then the people say that, okay, what happens for 4 by 4? What happens for 5 by 5? Yes. But then what should we do then? We have to have an argument that can be extended like this for all sort of these matrices, yes?
I have an intuition, but I don't know how well I'm going to be able to explain it. But let's say that we take the matrix with the zeros in the column and put it to the other side since it's going to be commutative, or you flip it with the...
That is a good idea. So it means that instead of checking this, let us check this one, yes?
Yes.
Yes, if you're comfortable with that, that's okay. If you can say at least one of them cannot happen, then that's good. It means that it is not invertible. So instead of choosing this one, you prefer to choose the other one.
Yes.
Yes, that's good. That was I was also thinking like that. So this is why UL and ZSM, and then you multiply it by this matrix ABC 0, 0, 0, and DEF. Yes. Okay, now you are claiming this is not possible to make it this, yes?
Yes.
Why this is not possible?
Since when you're going to now do the matrix multiplication, it means that every single, what's it called? On the column where the zeros are in the final product, every single number will be 0 as well. And since there is at least one.
Exactly. So for example, let us concentrate on the second column of this matrix. Yes? Only. Why on the second column? Because this occurred on the second column. Yes? And then if I ask you, can you calculate all the entries? By the way, this one is not here. This one is there. Yes? Yes. If you consider, if I ask you, can you calculate the second column of this product? I would say yes. Do you remember? I need to take the whole matrix and multiply it by the second column matrix. But if I do that, what is the second column matrix? It is 0, 0, 0. Yes? And you know that if you multiply a matrix by the 0 matrix, what is the answer? It is the 0 matrix. So, if I multiply this by the whole thing, the second column should be 0, 0, and 0. But the second column is 0, 1, 0. So it is inconsistency. There is no way for me to adjust these numbers so that it works. Is that clear? Or if it is hard for you, you just start multiplication. You take this one. If I ask you how do you calculate this entry, you will tell me that I will take the first row and multiply it by the second column, and I put it here. Here, there is no inconsistency, because if you do that, what do you get? X times 0, Y times 0, Z times 0, it becomes 0. Everything works fine. But when you go to the second one, you need to take the second row and multiply it by the second column. But again, you will get 0, but you see that this is 1. It is not possible to fix it. And I hope that you agree, even though this is a special case, but even the general case have the same philosophy behind it. Yes? Is that clear? Okay, so this is not possible. So if you have a matrix with 1, 0 column, it is not invertible. What do you think about 0 row? Do you think this is also invertible, or we can say not invertible, or sometimes invertible, sometimes not?
I think it's the same thing.
It's the same thing, but I think if you have a second row, this one work better. Yes, because then the second row will be 0, 0, 0 everywhere. So yes, that's the idea. So that is, I'm not saying that is a very important exercise, but I'm just trying to give you some exercises to develop some intuitions. Is that clear? Okay, now let us go to the theorem. As I promised you, I told you that whenever you can find one matrix satisfying both conditions, then that one matrix is unique. And this is why we are allowed to talk about the inverse rather than an inverse. And then we are allowed to assign a notation for that. Yes? Why do you think it is, if it is invertible, the inverse is unique? This is a very simple proof. I want to go through the proof because this is exactly at the right level of your knowledge. But you can think a little bit about that yourself. An invertible matrix has a unique inverse. So you see, invertibility is my assumption. Uniqueness is what I want to show. By the way, if you want to show something in mathematics is unique, one way, how do you feel you need to argue? I just want to hear from you before I spoil what I'm going to do. Yes?
Did you say one method is like if you can prove everything else is wrong, then the last
But is it
is right?
okay? But is that really practical? Because everything else means that I have infinitely options in front of me. Yes, Tino?
Possible. I just said one method of proving.
No, but one method of proving should also be practical.
I don't know if it's practical in this case.
No, but you're saying that I need to refute all other possibilities. You don't need to think about that this is not practical, because if I want to refute all other possibilities, I don't know, is that practical?
You can limit the possibilities in some way.
Okay, but this is not a very efficient way of thinking, yes? Of course, if you can narrow it down and say that this is only possibilities, then you are right.
Yeah, maybe since you have 4 unknowns and 4 equations.
No, there is no guarantee for unknown. This is completely generic. Because this is for any n by n matrix.
For a 4 by 4 matrix.
Yes?
Then you will have the same number of equations as unknowns.
Yes?
Then you will come to a definite
No,
answer.
but I just gave you an example. Do you remember we had a 2 by 2 matrix? In some case, we didn't have any answers. It was inconsistent. Do you remember this is the first example?
Yeah.
It's
So-
still, I have 4 equations, 4 unknowns.
Yeah, and then when you came to a definite answer, that answer is definite because there was no other answer.
Yeah, that's a feeling, but that's not a proof.
Okay.
Yes, that, I agree with you now. So you are saying that, by the way, there are some, so this is also not the case because I can repeat the same equation in the system. For example, how many equations we have here? X plus 1 is equal to 1, 2x plus 2y is equal to 2. This is a system of 2 equations and 2 unknowns, but how many solutions are there? Infinitely many. Because that's exactly the same equation I have repeated again. Yes? So I'm asking you about all pairs that satisfy these equations simultaneously. But this is not another constraint, because whatever you put here automatically satisfies the second one, because I just multiplied this by 2. So any pair that you can find and satisfies this will also satisfy this. So there's a system of 2 equations in 2 unknowns with infinitely many possibilities. And when we say, if you want to think in this line, it means that you need to think about all scenarios in which all systems have a unique answer if they do. Okay, but this is not the case. We have some equations, so you don't know what, because you do not have any control over the type of equations that you see unless you can sit down and systematically study them. Yes? This is one possibility. It was not wrong, but I would say it's still not that practical. Yes? Okay, but think about a general scheme. If you want to show that something is unique, what is the generic form of that? Because you know that in Math 4, the first chapter was talking about different types of proofs, but this is not any longer for the course. But can you think about another method? Generic method, not for matrix theory. if you want to show something, existence is different, but we assume that it exists, but why this is unique? How do you argue for uniqueness in mathematics? This I want you to learn after this discussion, yes?
Maybe if you take the result as in the inverse of that matrix, you backtrack the steps.
So first of all, you are again talking about only matrix theory.
Okay.
Okay, that's what I'm saying. So what you are saying is that, so somehow in the previous example, I erased that, but in the previous example, in the process of finding B, we felt that there is no other answers that we can get. Because when starting solving equation, we got a unique answer, yes? So you are saying that when we want to do it in practice, we found one unique set of answers for A, B, and C, and D, yes? But this, we don't know this is going to happen. Might be I give you a kind of matrix that will generate this scenario for solving. Yes? If you say that no, you should tell me why you don't believe this can happen. Yes? Because if this happens, I do not have a unique solution, I have infinitely many solutions. Okay, but I want to still hear from you. Okay. Try not just think about the matrix theory. If you want to show that something that we already defined, and it is guaranteed, its existence is guaranteed. You want to show that now it is unique. Any idea? For example, you want to say if there is a God, it's just the only God. What kind of argument you can show, I mean, in philosophy or whatever? You don't have any idea? The reason that I want to linger a little bit on that, because for me, it is natural, it is not very natural when I was at your age. I have been working with this for so many long times, it has become natural for me, yes.
I mean, at least for the one you showed, if you want to have an inverse matrix, there cannot be like a 2. You will either have a 1 or a 0.
No, you don't understand me again. Because you don't know this scenario can happen unless you guarantee me for some good argument that Babak, for any kind of matrices that are invertible, in the process of finding the inverse, you do not see such an equation. Because if you do, then you have infinitely many answers for x and y.
Yes.
So for example, assume that I have a 2 by 2 matrix and here it's x and here it is y and then z, t, okay? So how do you know that? In the process of this finding, you will not face this equation. And then I don't know, z plus 2w, so z plus 2t is 7 and 2z plus 4t is 14. Because if this happens, how many solutions do you have for this equation? Infinitely many. Yes? That's the point. How do you know that if the matrix is invertible, you will never ever come to a system like this? Because if you do, then you have infinitely many solutions.
Yeah, but since you want the inverse, you want an identity matrix, you should either...
Okay, I can check these numbers. So, I don't know, for example, 1, 0, 1, 0. Yes? So, 1, 0. Okay, might be, yes. So you are up to something. But I mean, in general, I can also...
That is impossible.
Yeah, that is
Then
impossible.
it will either be true or it will not.
Okay, but this is not a proof. You're forcing me to believe in that. Yes? Because you don't have all the options in front of you. This might be, I also think about, I can find another way probably. So for example, if I change these entries, might be, I need 2 1s and 2 0s, okay? Because in the identity matrix I have 2 1s and 2 0s. So well, how do you know that this will not happen, yes? Yes? I mean, I hope that you agree with me. This is not a decisive answer.
Yeah.
Especially if this is for simple case, but for that. But no, I'm talking in general. If you want to prove that something is unique, one idea, for example, if it says that, okay, there are two gods, you can explore the consequences of having two gods. And if it is against something that you already know, then you will say that, okay, this assumption of having two gods gives rise to contradictions. So this means that let us assume that there is only one God. Yes? Something like this. So here, I want to prove that this is not possible to have more than, it is not possible to have more than inverse. You say that, okay, let us explore what happens if we have more than one inverse. Is that clear? And if it gives rise to contradiction, it means that that assumption cannot be true. Because assuming that assumption, logically, I came up with a contradiction. Is that clear? This is called proof by contradiction. Yes? So if you want to prove, for example, let me just give you a number. So you cannot force me to ask. This is a very simple example, by the way. So only think about natural numbers, make things very simple. And then I say that, okay, I squared a number, a natural number, the answer is even. Okay? What can you say about the evenness or oddness of the number before being squared? I square a number, a natural number, the result of a squaring number is even. What can you say about the number itself? Yes?
It's even.
It's even. But why?
Because I guess you can use the formula for a.
No, that's exactly what I wanted to say. Is it not working? Let us see. Okay? So I'm saying that I have a number. What is guaranteed is that a squared is even. When I say I have a number, it means that I am only working here momentarily in n. So I know that a squared is even. You are claiming that a is even. Yes? And I agree with that. That's 100% true. But this is a very simple example to understand that proof by contradiction is really sometimes necessary. Okay? And unavoidable. Okay, so how can I prove that? So, how can you prove this, by the way? So you cannot say, I feel, of course, here feeling is working good, and it's correct. But why? Yes?
So you could see the other alternative. Would it be logical to say that A is uneven, and you can show that that would not be possible, and then?
No, that's true. So you agree with me that we have to do proof by contradiction?
If that's what you want.
No, I just want, because yes, that's correct.
Yeah.
I just want to say that because Tino said that we go for a direct proof. Yes. So what do you do? When I say a squared is even, what do I know? I know that a squared is 2 times an integer. Okay? So when you say a squared is even, means there exists an n in the set of natural numbers such that this happens. Yes?
Yeah.
But now you want to prove that a is even. What do?
You take the definition of an odd number, and then if you square it.
Okay, so you are using proof by contradiction. That's what I'm saying. Proof by contradiction is part of a logic, is not part of mathematics. So every human brain works like that. Yes? So I'm just telling you that direct proof will not work here. Because if you want to say something about A, the direct proof needs to take a square root. Yes? If a squared is 2n, and I want to know something about a, the natural direct proof is to take a square root, which I end up here. But this is the dead end. I cannot continue and say, look, because a is equal to a square root of 2n, a is even. Do you agree? Do you agree or not? Because for being even,
for being even, A should be a multiple of 2. But this is not, that's what I'm saying. You cannot say that, look, I want a multiple of 2, but this is not a multiple of 2 because it is not like a multiple of 2. This is not working. Do you understand that? Because at the end of the day, we know that A is a multiple of 2, even though this is also correct. Yes? Because this is not wrong. When you say A squared is 2n, definitely A is equal to a square root of 2n. But because this does not look like a multiple of 2, we cannot say that, okay, this is not a multiple of 2. Do you understand that? Because it is possible for this number to be a multiple of 2 sometimes. How? For example, I choose n to be 4. If n is 4, then 2 times, n to be 8. Then it becomes 16, square root of 16 is 4, 4 is a multiple of 2. So you see that because you prove this, which I agree totally correct, if you conclude because A is in this form, therefore A is not in this form, this is wrong. Because it might happen that not only A is in this form, but it's also in that form. Is that clear? That's what I'm saying. For example, if I say that A plus B to power 2 is A squared plus B squared, you cannot say because A plus B to the power of 2 is A squared, technically speaking. You cannot say that, no, this is the correct one, so this is wrong. Yes? This is because you say that, okay, this is the correct one, so this is wrong. I usually use that when I'm teaching you. Okay? But in principle, if you want to say this is not correct, you need to bring a counterexample. Not because of the form. So I cannot say, because who knows, might be, this can also be reduced to this one. If I insist, you have to tell me that, look, if you insist they are equal, this is your example, it does not work. There is no way out of it. Okay? So the indirect proof is actually a very, very strong tool in our hands when we want to prove something is unique, especially. There are different scenarios that we can use proof by contradiction, and sometimes it is called indirect proof, but usually if you want to prove something is unique, this is usually mainly the theme. You say that, okay, let us assume it is not unique, let us explore then what happens. Yes? And you try to convince people this gives rise to a contradiction. So let us just do that. So might say that A is invertible. A is invertible. I want you to learn this way of proving. So invertible. Claim is that the inverse of A is unique. Okay? So let me write all the proof here for you. So the proof. So what should I write? Let us assume it is not the case. I am claiming that the inverse is unique. Let us assume for the moment it is not the case. So it is not unique. So then what happens? What does it mean when you say it is not unique? It means that there is at least two of them. Yes? So this means that, therefore, there exists distinct matrices B and C such that what? Both are inverses of A. Yes? So I am claiming that the inverse is unique. If you don't agree with me, then you have to agree that there are at least two distinct ones. Yes? Is that logical? No. Let us explore the consequence of this assumption. Okay, by the way, let me in a scratch work write what I mean. So in here, when I say B is an inverse for A, what do I mean? I mean AB is equal to BA is equal to I. Yes? If you don't agree this is the only one, then it means that you also agree that there is another one. But if there is another one, what does it mean? Yes?
AC.
AC is equal, CA is also equal to I. So, I assume that there are two distinct matrices, B and C. They are not equal, but both of them satisfy these four equations. Yes?
Wouldn't that mean that AC equals CA equals AB equals BA?
Yes. Yeah. But that's not that's not a contradiction in itself.
Okay.
I need to see that there is some contradiction going on. Okay, but the trick is simple. Then, let me start with B. Do you agree that B is equal to BI? You cannot say no here because we explored, this was a proof, this was a theorem, yes? But let me now, instead of I can keep B, and instead of I choose, let me see which one is working here. So I choose AC. Yes? Do you agree? So, you cannot criticize this because B is equal to BI, this is a theorem, and if I is equal to AC, this product is equal to that product. Okay, but then matrix multiplication is associative. So instead of having parents bracket here, I can put them here, yes? So then what happens? This becomes BAC. Yes? But what is BA? BA is also in my list. It's I. Yes? So this is I now. So then it becomes I times C. But what is I times C? It's just C. So this means B is equal to C. And that's a contradiction. Why? Because I assume that they are distinct. Yes? So I say that, okay, my claim is that the A inverse is unique. You say no. If you say no, it means that you have to admit that at least there are two distinct matrices B and C with the same properties. Yes? But if you accept these, then you have to come up with the fact that B has to be equal to C. So on the one hand, B and C are distinct. On the other hand, you have to accept that B and C are the same. And these two cannot happen simultaneously. So this is, you see, it's a very practical. So the proof is just one line and adding these two ideas. So this is not, we are refuting all other possibilities. We are coming with a contradiction. So we assume that this is not the case. We explore the consequences of this assumption. If I come up with an inconsistency or contradiction, it means this contradiction is the direct implication of my assumption. Yes? So it means that my assumption is not correct because it gives rise to contradiction. So this is indirect proof or proof by contradiction. Is that clear? So, okay. I just talk about that and we just end here. So this is why all these gymnastics we did, now finally we can use this symbol. So I want you to understand that if you really want mathematically to do it correctly, you have to go all through all these things, understand them, and then you're allowed to assign a symbol for it. Because now, if A is invertible, I can talk about the inverse. When there is only, if it is invertible, there is exactly one inverse, so I am allowed to give a symbol to refer to that idea, yes? Okay, so from now on, don't take this for granted. In order to be able to use this relation, first you need to convince yourself about the existence of A inverse. And in that case, this is true. Yes? So I don't know if I have written here any remark or not. Okay, so let me just read it for you. So let A be an invertible matrix. We learned that its inverse is unique. This unique inverse of A is denoted by A inverse. Therefore, if A is invertible, then this holds. Note that one is not allowed to use A inverse unless the invertibility of A has already been confirmed. Yes? Because we saw that some matrices are not invertible, some of them are. You're not allowed to just use A inverse before confirming that this exists. Yes? Okay. I think I will stop here. We will continue this lesson. This is a very important lesson, actually. Any questions? Okay, thank you.